Hello, my name is Cooper McAllister, and this is the second development log for the LaTourneau University Space Program Advanced Remote Ignition and Evaluation System. So at this point in time, the first revision of the PCB design is complete, so I'm just going to go over that a little bit, talk about some of the additional design decisions that were made in the design of the PCB, as well as some next steps going forward. So just for an overview of the project, um, I said a lot of this in the last video, but I'll go over it again. We're making a remote controlled rocket motor ignition and measurement system to ignite rocket motors and then measure forces from sensors to characterize the efficiency of the motor and nozzle. And this involves a custom PCB with both analog and digital components. The entire design is centered around a microcontroller, specifically the Raspberry Pi Pico. And the priorities for this design or for this project are safety, reliability, and ease of use by future team members so that after I graduate, other people in the LaTourneau University Space Program can use this device easily. So some design simplifications that were made since the last development log. First of all, as far as analog digital conversion goes, I decided to use the HX711, which is a common load cell analog digital converter and amplifier. So this is the specific breakout board I chose. It's from SparkFun. This is a chip that's commonly used for load cells, and this breakout board allows us to easily integrate that into our design. So we're going to have that on the PCB for our load cell is going to be the primary sensor, and then if we want to add any additional sensors in the future, there's some extra pin headers on the PCB that will let us do that. And then as far as the number of ignition channels, the previous remote ignition system had 3 channels, and we decided to go with 2 just because it's cheaper and simpler. So there's 2 pyro channels because we really don't need 3. So there's 2 pyro channels and then 1 LED channel, and that's for LED safety lights on the test stand to alert people that a test is being run. And then finally, I realized that safety is a very important part of this design because we're dealing with potentially explosive rocket motors. So the best safety features are ones that are very simple, straightforward, and reliable. So we want to have features that prevent both accidental ignition of the rocket motors as well as thermal protection of the circuit board and its components so that nothing breaks. So as far as those safety features go, the first one is the arm switch. I've designed it so that current can only flow through the MOSFETs to the igniters when the arm switch is on. So when the arm switch is turned off, that entire current path is disconnected, and no software, no nothing can make current flow through the igniters. Only when the arm switch is on can current flow through the igniters. So that's one of the primary safety features. So you would essentially set up the test stand, get everything running, and then the very last thing you do before you leave the test stand would be flip that arm switch and then go a safe distance away to actually remotely control the igniters. And secondly, I've added a circuit breaker, and I designed it so that all the other components in the current path of the igniters are rated for a higher current rating than the circuit breaker trip current. So that breaker is a 15 amp breaker, and then all the PCB traces and the MOSFETs and all that is rated for a higher current than that. So that means that the circuit breaker will trip before any of the PCB traces or components get hotter than they should. Finally, for the case design, this is kind of the last thing I had. We went with a waterproof hard case. Yes, this is the case that I selected. So orange, nice and visible. And this is going to be a lot more durable than anything that's like 3D printed or anything like that, and probably a little bit more resistant to heat and flame and explosions. Obviously not as good as like a metal case or ammo can or something like that, but it'll be pretty good. And then we're going to put the arm switch and the buzzer on top of the case. Sorry, the light is actually not going to be on the top of the case. It's going to be on the test stand. but we'll have the arm switch and the buzzer and the circuit breaker as well on top of the case. And then all the connectors for the igniters, the sensors, the LED, and the radio antenna are all on one side of the case. So they're all on one side of the PCB, and then that just is going to be right next to the edge of the case with holes. So that means that we only have to drill holes on one side of the case. That makes it a little bit more simple. And then as far as the battery, we decided to go with a 12-volt drill battery. It's easily rechargeable, and we're actually going to I don't know if I still have it open. This is the drill battery. We're actually going to buy this drill and then just cut off kind of the bottom part of it. So then we'll have the battery as well as the socket that that battery goes into. And we're just going to put that whole thing inside the case. So then it'll be very easy to remove that battery and charge it. And yeah, so that's kind of the big design things I wanted to go over. I'll go ahead and show you the schematic and the PCB a little bit. Here's the finished PCB just so you can get a look at it. So I'll go over the schematic real quick. Just going from basically top to bottom, left to right, we have the battery coming in here. There's 4 terminals on this connector, and these bottom 2 terminals are going to be connected to the battery, and then these top 2 are going to be connected to the arm switch. So when the arm switch is turned on, current is able to flow from the battery through the arm switch and then to this pyro power, which is what's actually powering the 2 pyro channels. So we have one pyro channel here and the other pyro channel here, and both of these channels have a voltage divider circuit to measure the resistance of the igniter, and then also a indicator LED so that it's easy to tell when those channels are being turned on and off. That's going to be very easy or very helpful for writing the software and debugging things to be able to see when those pyro channels are on without actually connecting an igniter or a multimeter. And then we have a 5-volt regulator here that's providing power to the Raspberry Pi. You see here through this Schottky diode. We have some extra GPIO pins going to the pin headers here. And then all the you can see all the pinouts there. We have the SD card here, micro SD card port. This is the buzzer. This is the LED. Both of those are controlled by MOSFETs, just like the igniter channels are controlled by MOSFETs. And the LED, as well as the 4 load cell sensor pins, are connected to this connector. And those load cell pins are coming from this HX711 breakout board. And then we have finally the NRF24L01 radio here. So you can see this on the PCB. So we have the Raspberry Pi here kind of in the middle, the arm switch and battery connector here. I tried to put as much silk screen as possible to make it easy to use this board, even if you don't have the KiCad files to look at. So I just said, use a 15-amp circuit breaker, and then I put some other labels on here for kind of where stuff connects, as well as the SPIO or SPI GPIO pins on there for reference. And then, yeah, so we have our power channels, buzzer connector up here, power channel 1, power channel 2. I'll turn on these models so you can see where the LEDs are. There's indicator LEDs for both power channels, and then the 5-volt power indicator. The HX711 breakout board is going to go right here. The Nerful radio is going to go right here. And then the SD card is going to go here. We have the test stand connector. That's those 6 pins, 2 for the LED and 4 for the load cell. That's going to go on this side. And then, yeah, those extra GPIO pins as well as the SPI pins are all broken out to pin headers here. So those are easy to access in the future. And yeah, that's pretty much it. Here's the PCB design. I'll show you just a little bit here. So the back copper is mostly all a ground plane, and then we have these large traces. This one's for the LEDs going out here. There could potentially be a lot of current through there. I kind of tried to future-proof this because I don't know what if we upgrade the test stand in the future, we might have different LEDs than we do currently, so might have potentially a lot of current flowing through here. So I made that trace nice and big. And then this is the pyro power trace, sorry, going to the two power channels here. And then, yeah, basically the rest of that is all ground plane. There's a 3.3 volt trace going down here. There's some odd traces here and there. And then on the front copper, that's where really all of the other traces are. We have our 5 volt power coming from the regulator. This is the regulator right here. And then that's going really just to this pin header here and to the Raspberry Pi through the Schottky diode you can see right there. And then that the 5 volts, or sorry, this is the 12 volts from the battery going to the buzzer. It's a 12 volt buzzer. And then we have our data lines. These are all our SPI data lines going to both the SD card here and the radio. Traces for the HX711 load cell board and just all the other traces there. And then, yeah, we have the silkscreen layer. Like I mentioned, I tried to make it as easy as possible to use this board, even if you don't have, intricate knowledge of how it was designed. So yeah, that's the current design. This is the parts list. I probably should have mentioned this earlier, but these are all the parts we have selected. We are going to try to order everything from DigiKey pretty soon here. That actually leads into my final slide, which is just the next steps. So we're trying to get this test stand working as soon as possible for our propulsion team because they want to start characterizing motors as soon as possible. And so we're ordering the PCB and all those parts ASAP. It's Sunday today, so we're going to order them tomorrow. And then should be getting here in about a week. And then we'll need to solder the PCB. And then the main thing is going to be programming the Raspberry Pi, and then also working on the remote controller. That is mostly complete. We're going to reuse the old one from the previous test stand. It has the same exact radio as ARIES, so it should integrate very easily. But I'm going to replace the case for it just because the current case is a little bit old, a little bit jankily assembled. So gonna just make a new case for that, and then obviously programming that as well because unfortunately all the code for that was lost. And I don't know who wrote it or where it is. So just gonna program everything fresh, and yeah, that's gonna be the bulk of the work moving forward. And I'll hopefully be able to make another update or two about how the programming is going, and also when we get the PCB ordered and get everything soldered on and up and running. So yeah, all right, thank you. Thanks for watching. Hope you have a good one.